Hello, everyone. Thanks for coming. My name is Seemann, and if you want to know more about me, there's information there on blog.plur.dk. So this talk is about software development productivity. So that's a problem that we often need to solve. At least, most of us don't really feel that we are as productive as software developers as we'd like to be. And in general, our managers and other stakeholders tend to believe that we're not nearly as productive as we ought to be. So that's the problem that I'm going to try to address today. And I'm not going to say, or I'm not going to claim that that's the only problem that we have in software development. I'm also not going to claim that the solution that I'm going to propose is the only way to address that problem. Far from it. But we just have to start at one place and sort of work from there. So why aren't we as productive as we'd like to be? There's probably lots of different reasons for that. But one of them is that we spend a lot of time reading existing code. You could say we waste a lot of time reading existing code. So Robert C. Martin, for example, writes in one of his books, the ratio of time spent reading versus writing is well over 10 to 1. And I don't know where he get those numbers from. I think he may just pull them out of a hat. But I think, still, the ratio is, sounds, fair. Let's just go with that for an example anyway. It's a way to talk about things. What happens to your productivity if this is true? And where should you prioritize your effort? Now, one way we can try to illustrate that is with a little graph like this one. So I have, 10 orange boxes representing the time that you are spending reading code, and then one green box representing the time you're spending writing new code. And that's a 10 to 1 ratio. So often when you have software vendors or language designers or library authors talk about productivity, they will often tell you that you need to, they will often tell you that they have solutions for you that will enable you to write code faster or, write code in a more efficient manner. So if you just, hypothetically imagine that you could, decrease the time you have to spend writing code with 50%, or you can actually, well, that's a doubling of productivity. But if you could do that, that's sort of like a hypothetical experiment, that thought experiment. That's not actually going to happen. But that would mean, that's a 50% reduction in the time you spend writing code. And as we can tell from this graph, that's probably not really, that sounds like a lot, but it's really more like 4.5%. And 50%, that's probably not going to happen. That's not really realistic. You can get improvements in efficiency in terms of writing software and so on, but probably not by 50%. Now, don't get me wrong, I'll take all the improvements that I can get. So, if I have a vendor that comes out with a new IDE that I think is better than the one that I'm using at the moment, I'll take that. If there's a new language that comes around that, or, language features that come around that makes me more productive, fine, I'll take all of that. It's just that I don't think we should imagine, or, we shouldn't be under the illusion that those things are really what's going to matter in terms of our productivity. If we want to be more productive, there is the elephant in the room is we have to do something about readability. If we can, decrease the time we spend reading existing code, we can actually become much more productive. So that's what this talk is about. Now, how do you write readable code? And how do you determine whether code is readable or not? That's not an easy question to answer, but let's try to look at an example. So here's some example code, and I would claim that this is readable. And then someone else would come by and say, well, it's completely unreadable because it's C# code. Or maybe I put the curly brackets in the wrong place, and that's unreadable for those reasons, or whatever. But that's not really gonna help us to move forward if we have those discussions that are basically, based on opinion. So one person could say, I really like this. This is readable code because I wrote it. And then someone else would come by and say, I don't like this at all, for various reasons. And then the first one will say, but it is readable. And the next one will say, no, it's not. So this kind of kindergarten, level of, discussion is not really, what's going to take us further. So we need to have we need to instrumentalize the way that we can talk about these things. So we need to have a vocabulary that we can use in order to figure out, is this readable or not. So what I'm going to try to do is to talk you through what happens in the brain when we are exposed to code like this. So all code that I'm going to show you here is from my book, Code That Fits in Your Brain, Code That Fits in Your Head, sorry, which is right here. And it's the same code base that goes as an example all the way through the book, and that's also the code that you're going to see here. It's an online restaurant reservation system, which is a REST API. Never mind, that's not really that important, but just if you wanted. All right, so what happens if we are confronted with code that we haven't seen before? So what most research seems to indicate is that the brain starts to engage in a process called tracing, or basically cognitive compilation. It's as though we in the brain are trying to run a little interpreter or an emulator, trying to understand what happens in this code, what happens if this value is that, and so on. So the brain tries to make sense of these things. I'm going to spend some time talking about this code, and the point is I'm trying to talk about what happens in the brain and how we read code. So it sounds like I'm walking you through the algorithm, which is actually not the point. I'm walking you through how do we actually read and understand code. So one of the things we might notice is, first of all, okay, so this is a method, it has a name, it's called allocate. It returns an IEnumerable of table, takes an IEnumerable of reservation as input. So if there are any people in this audience who are not, .NET developers, IEnumerable is basically just a collection. And reservation and table are, objects, domain objects that we haven't seen yet. I'm actually not going to show you those. But then, when we start tracing through the code, this cognitive compilation, we'll notice that one of the things that happens here is that there's this object called allocation, which is a list of table. And a list object in .NET is something that can change state. We can, erase all the elements inside of the list, or we can add new things to it, or we can remove or reorder things and do all sorts of things. So if we're trying to understand what's happening in this code, we might notice that, hey, this is something that I need to keep track of. This has state, and this state may change. And since I haven't scanned through the rest of the code yet, I haven't actually figured out whether the state of this object may impact whether I go in one way or the other. So, keeping track of state is really important, because otherwise I can't, cognitively compile the code. So that's one thing to keep track of. Now, there's a for each loop, and if reservation is empty, we just fall all the way through, and we don't execute any of the indented code. On the other hand, if we have at least one object in reservations, we will now try to find a table in the allocation that fits a particular reservation quantity. And the find method will return null if it can't find anything, so we have to check for that as well. So this little thing where it says if table is curly brackets, that's sort of like a C# little pun, basically, that means if table is something, basically meaning if table is not null. So we're checking for null there, and if it's null, if it's not something, again, we fall through and we don't execute the indented code, but otherwise we do execute the indented code. So we remove a table, we remove the table that we found from the allocation and add it back in, but then now with the reservation associated with it. So there's a little bit of local state mutation going on here, but it's sort of like, it's okay, we're keeping track of one thing in our brain, and that seems to be fairly okay. So to summarize, there are three pathways through the code, and some of you will probably also already recognize that this kind of analysis is called cyclomatic complexity. So cyclomatic complexity basically gives you this idea, how many different pathways are there through the code. And you can think of that as sort of like three different execution paths that all coexist at the same time. So it's almost like 3 dimensions sort of superimposed on top of each other. So if we have cyclomatic complexity too large, we're probably going to get overloaded mentally if we're trying to understand what's going on. And likewise, if we have to keep track of too much stuff, too many variables like allocation, then we're probably going to get overloaded. Our brains will probably not be able to perform that cognitive compilation of the code. We're not able to trace through the code. So the problem is, or the question is, now we have at least 2 ways of quantifying, the complexity of code. I have cyclomatic complexity, and I also have this thing where we can ask ourselves, how many objects do we need to keep track of in order to understand what's happening? And it seems like this code is, we have cyclomatic complexity of 3, and we have basically 1 mutable object that we're keeping track of. So that sounds like it's probably okay. And I would claim that this is okay because the threshold is a little bit higher. What fits in our short-term memory? And there's a lot of research that seems to indicate that maybe we can keep track of about 7 things in our short-term memory. This is based on a paper by George Miller called The Magical Number 7 ± 2, which dates back from 1956, based on lots of experiments with people, where they were asked to keep track of various different things in their short-term memory. So the limit, sits around 7. We can keep track of about 7 things in our short-term memory. Now, Miller didn't. Miller wanted and asked people to, keep track of various different things. He asked them to remember random numbers, for example, but you could also ask people to remember other things, for example, colors and so on. So it doesn't have to be numbers. We could, actually think about these things as just, what we call chunks of information. So it doesn't have to be, very primitive numbers like digits, for example, but it could actually be words or colors or, things in the physical world. So while I keep talking, I'm just going to switch over here and start a little animation. So we can keep track of about 7 things in our short-term memory. When you start a completely new code base, when you write the first hello world line of code, that may be one thing, and that sort of fits in your short-term memory. But as you add more and more decisions, more and more features to your code base, you very quickly come to a point where there's more than 7 things going on. A realistic code base probably has 7,000 things going on, or maybe 7 million things going on. There's way more that you can fit in your short-term memory. So the question is, how do we deal with that? How do we deal with the fact that there's going to be much more going on in a code base than fits in our short-term memory? So basically, as far as I can tell, we have 2 options. Either we can rely on long-term memory, or the other option I'll get back to in a moment. So I think relying on long-term memory, long-term memory is a completely different kind of beast. Long-term memory, no one really knows exactly what the capacity of it is. It's not that precise. You can actually warp and forget things or remember things wrong and things like that, but it seems like it has a really big capacity. And I remember I was once engaged with a client who wanted me to help them with their legacy code base. And I got to interview some of the people on the team, and one of the team members that I got a chance to talk to was the newest member of the team. He'd been there for two years. So I asked him, so when you started, it was still recent in his memory, when you started, how long did it take you before you could, you felt that you could do something in this code base on your own without help from your peers? And he said, well, that took me three months. He didn't even hesitate. He said 3 months. So I think he spent those 3 months, painstakingly trying to commit the structure of that code base to his long-term memory, which is, quite, maybe not infinite, but arbitrarily large. So that sort of works. It's just that it's a lot. It takes a lot of time, and this is one of the reasons why we spend a lot of time reading existing code, because there's just a lot of stuff to commit to your long-term memory, and in order to, efficiently, commit something to your long-term memory, you have to, study it and keep on repeating the exercise in order to understand how things work. And another problem we have with long-term memory is that once we've committed something to long-term memory, it sort of tends to stay there. So once you've understood how, the structure of a large-scale code base, once you've committed that to long-term memory, then if one of your colleagues come by and changes things, the code no longer fits the mental image you have of it, and now it becomes even more difficult to reconcile what you have in your long-term memory with the current state of the code. So again, you have to sort of reread things over and over again. So while it's possible to work with a code base where thousands or millions of things are going on, you sort of have to rely on your long-term memory, and that slows you down. So that's one of the options to deal with this sort of problem. Now, the other option to deal with this problem is to say, well, what if we decided that instead of relying on long-term memory, we could rely on our short-term memory? That would make a lot of things much easier, because our short-term memory is sort of ephemeral. You load something into your short-term memory and you keep it around long enough that you can do whatever it is that you need to do with that information, and then as soon as you go and do something else, you forget about that stuff as well. So what if we could structure the code in such a way that we could load it in, when we look at it, it all fits in short-term memory. And then we can work with it. We can do what it is that we'd like to do with that, using our short-term memory. And then once we've, committed the change to Git and pushed it away, we can go and do something else, and we forget about it. And that means, the next time you come by and look at that code, it takes a couple of minutes to sort of reload it into your brain again, to your short-term memory. But you don't have to engage your long-term memory. And that also means that if someone else, if one of your colleagues came by at the same time and changed that code, you're not being confused because you've already forgotten about it. So when you see it again, if the colleague also tried to respect the cognitive constraints of our short-term memory, then you should be able to read the code and deal with it using your short-term memory. Now, while I've been talking about this, you've noticed that this grid is starting to take shape here. I added a lot of those chunks, and I just keep, this simulation just keeps on adding things. And you can see that it starts to resemble, honeycomb. So what happens if we say, well, we need to, isolate at most 7 things, and just deal with that. So I'm going to switch back here, and if we isolate at most 7 things, we get a figure that looks like this. So I call this a hex flower because it looks a little bit like a flower, but just made up out of hexagons. And you can think of that as each of those cells representing basically a register in your short-term memory. So your short-term memory is a byte, a 7-bit byte, that is. That was a thing once. So that's what you have to do with. So if we want to instrumentalize or make it a little bit more objective in the way we talk about whether or not code is readable, we should think about how can we respect that cognitive constraint. And we can use this little figure here as a symbol of that. So just to be clear, I'm not saying that the magical number 7 plus minus 2 is not 7 is not that magical. Most of what I'm going to say here is doesn't really rely on the number being exactly 7. It could be 5 or 9 or whatever. But 7 gives us this nice figure as well. So I'm just going to go with that. All right. So when we look at code, we are going to look at code at various different levels of abstraction. And the cognitive constraints that we can only deal with 7 things in our short-term memory, that always applies. Our brain doesn't care about the level of abstraction of the code that we are looking at. So if we want to respect the limitations of our short-term memory, we should always structure code so that there's at most 7 things going on, because otherwise we can't trace the code. But there's going to be, deeper levels of abstraction. So if you're looking at things at a high level of abstraction, we also understand that each of those cells, let's say the upper right one, that's going to contain, more complexity. So if we want to zoom in on that, again, at that level, it needs to respect the constraint that we can keep track of most 7 things. So again, we should be able to do that at all sorts of levels of abstraction. So again, if we zoom in again, we might actually encounter some real code. So I chose to start with this create method because this is sort of like the lowest level of detail. There's not a lot of abstraction hidden behind this. So this is a method that sits on a class that has the responsibility of saving and retrieving data from a database, from a SQL Server database. So you could ask yourself again the question: is this code readable? Does it fit in your short-term memory? And now that we have a few ways of instrumentalizing or quantifying these things, we can start to ask those questions. For example, what's the cyclomatic complexity of this code? And the cyclomatic complexity is 2. There's 2 pathways through this code. Either reservation is null, and that results in one outcome, or reservation is not null, and that results in another outcome. And I know that there might be exceptions thrown, so I'm just going to ignore that for now for various reasons. So we can say the cyclomatic complexity is 2. So that's sort of like 2 parallel dimensions that exist superimposed on top of each other. We can probably keep track of that if we can keep track of 7 things. This method represents 2 different things. So that's one thing that we could try to do. So in that, if we choose to use that measurement, we could say this is readable because there's less than 7 things going on. But there might be other things going on. So what we can also do is, I talked about this thing where we do tracing and we try to keep track of, object state. So what we can do is, as a very crude, kind of measurement, we can count all the variables. So we can say, so there's the restaurant ID, that's a parameter. That's a blah. That's a thing we need to keep track of. There's a reservation, there's another parameter, we need to keep track of that. There's something called a connection string that we use to create a SQL connection. So that's a string. It's actually a read-only property. And for those of you who are not C# developers, a property here is just a glorified class field. So just think of it like that. But it's read-only, so it can't change, and strings in general don't change. So this just contains information about how to connect to the database, and we use that to create a connection object. And I'll just keep on counting here. Create reservation SQL is another string that contains the actual T-SQL code that will be executed against the database. And we use that and the connection to create a command object. So, and then from there on, there are no more variables. So that's all the variables that are in scope here. So after that, if we trace things, how many things are actually changing state? So the command object changes state 6 times because we add, parameters. We bind each of the parameters to values, but it's quite easy to follow. And then, towards the end, where we go con.openAsync, we actually change the state of the connection as well. So it, starts out being closed, and now it's open. But it's quite easy to follow because there's not too much stuff going on. And so again, if we think of 7 as being the limits that we have, there's fewer things going on here, so it fits in our head. Before we move on, you might say, okay, but really, something like restaurant ID, the one that I've labeled 1 with the number 1. That's an integer, that's immutable. It's not going to change state, so we don't really need to keep track of the state of it because it's not going to change. And the same thing goes for the connection string and the create reservation SQL, those labeled 3 and 5. They're strings, they're immutable, they're not going to change. So really, if you want to be a little bit more sophisticated, you can say, all right, so we only need to keep track of 3 things: reservation, con, and command. But then again, if you go and actually read the implementation of the reservation class, you'll notice that that's an immutable object. It's a value object, and it's a domain object that I created in that particular way because I know that immutable objects have a lot of benefits. And one of them is that you know that they're not going to change, so you don't really have to expend that much mental energy to sort of, when you're trying to understand what the code does, you don't have to worry, does it change? Because it's not going to change. So really, there's only 2 things that will change: the command object and the connection and the command objects, and they actually do change here. So if we want to be more sophisticated, we could argue there's only really 2 things going on. So this is very readable. For that reason, it fits in your head. But if we're just being crude, we just count all the variables because this is easier. You don't need a tool for that. You can just do that when you're looking at the code. So we can try to enumerate all of those, or we can try to assign each of those variables to each of those cells in the hex flower, and we can say, okay, they all fit. We have room for 7. We only used 6. So we're good. This fits in our head for that reason. All right. So the hex flower here is basically a symbol of things that fit in your head. Now, I showed you, I started by showing you this create method because that's sort of like the lowest level of granularity. There's really not a lot of user code hidden behind that thing. There's only framework code like SQL connection, SQL command, and things like that. And you typically don't go and read the code of framework code. But then you might say, well, but at a higher level of abstraction, we have code that calls that create method that we just looked at. And if there's 6 variables involved in understanding what the create method does, doesn't that compound, if we look at it from the next level? So if you imagine that we're looking at it from the next level now, and in one of those cells we have this create method sitting that uses 6 variables in itself, and then we have something else sitting in one of the other cells because we are calling another method, and that maybe represents complexity of 4, and then you can add 10 and 4 together, and that that blows the budget. So you can't do that. So it's very, very important to make sure to design the code in such a way that when you zoom out and look at things at a higher level of abstraction, what looks a little bit complex at the detail level should just become one thing. It should become one chunk. You should somehow be able to represent that in your brain as being just one thing, because otherwise it doesn't work. So you should be able to zoom out one level, or you should be able to keep on zooming out in your code base. And every time you look at a higher level of abstraction, you still have to take into account that the brain is organized in the way that it does, and it has the limitations that the brain actually has. So I'm going to return to the problem or the question of, how do you assign things so that they don't leak their complexity. But I'm going to do this in 10 minutes, 10, 15 minutes. I'm going to talk about something else first. So again, we looked at the most detailed level of granularity. But on the other hand, we also want to be able to zoom out to, basically maybe the entry point of the application and say, we also need to organize code at a very high level of abstraction so that it fits in our head. So if you've ever worked with ASP.NET Core, you've probably seen code like this. This is basically generated by a wizard. I didn't write this code myself. I just had Visual Studio write it for me. But we can still sort of analyze and see, does this fit in our head? So first of all, if you know a little bit about ASP.NET Core, you don't have to for this talk. But if you did, you probably know that all the interesting stuff will happen inside a class called startup, and we'll look at that in a moment. But otherwise, we can try to enumerate, what else is going on here, and there's really only 3 things. So that's good. We don't have a problem with this main entry point. Now, if we're interested in the startup class, we want to be able to have a look at that. So we're looking at a thing that has a slightly, a slightly more granular level of abstraction. And again, if we hope that this code is organized in the same way that it respects our short-term memory limit, we shouldn't have, if we go and look at startup, we shouldn't have to remember that there's arcs and web builder involved. So it's also very important to make sure that whenever you zoom in on something, all the surrounding stuff sort of goes out of scope in terms of what you have to require of your brain. So this is the public API of the startup class. We can just, again, simply enumerate there's 2 methods here. There's a constructor that takes a configuration object and then later on exposes that configuration object. So again, if we try to enumerate that, that's basically 3 things going on. So that fits. Now, configure services, again, I'm not trying to talk you through how this application is organized. I'm mostly trying to give you some examples of, how do you organize code so that you keep on respecting that there can't be more than, approximately 7 things going on. So again, you can try to have this little quantification where you can say, well, how can we discuss whether something like what we're looking at right now, is this readable or not? So you could ask again, various questions like, what's the cyclomatic complexity of this thing? How many, alternative pathways do we have through this code. And there's no branching, there's no looping, so we basically just run all the way through. I know there's a little bit towards the end there that you can't see. I'm going to reveal that in a moment, but there's no surprises there, trust me on that. So cyclomatic complexity of 1, that's as low as you can get, so that's fine. We can also try to enumerate, again, just the crude thing of enumerating all the, the variables that are involved, and it turns out that we have 6 of those as well, so we're good on that account. Now, I want to stress here that these measurements that I'm talking about, these attempts at quantification, like cyclomatic complexity or counting the variables, other things like that. You might also want to look at lines of code. You probably have to divide that into segments in order to make it fit with 7, but that's a different story. Now, but what I want to say about this is that this is. These things are not there in order to be rigid rules. These are, tools you can use in order to give yourself a vocabulary so that you can discuss things with your colleagues. If you want to have a discussion with a colleague, where you feel that a particular method that you're looking at is growing too complicated, and you want to split it up into a couple of helper methods, and the other your colleagues says, well, I don't feel that way. Again, if one says I feel this, and the other one says I feel that, you're not having a discussion. You just you're at the kindergarten level. So you need to have some sort of vocabulary where you can talk about these things, and this is a way you can talk about these things. Now, again, you have to agree on the premise here, but it moves you a little bit closer to being able to actually have good discussions about code. All right, so I would say this code is readable for those various reasons. So as you can tell, towards the end here, there's nothing more interesting going on there. So towards the end, what we basically have is a table of contents. So we're still working on a very high level of abstraction in the sense that there's nothing that really tells you what's going on in the details of the system. But it's sort of like it's like a table of contents that tell you where can you go if you want to learn about various different things. So for example, if this is a REST API. If you want to know whether or not you need to log on in order to be able to use this REST API, or if it allows anonymous access, you might say, okay, configure authorization. That sounds like a reasonable next place to visit. So maybe you want to go and have a look at that method. Now, when you do that, again, all this stuff that surrounds it at the moment shouldn't, be important. If you go and look at configure authorization, only what happens inside of configure authorization should be, important. So what you see is all there is, as Kahneman says. The same thing goes with configure repository. If you want to know about the persistence system in this code base, you might go there. And again, when you go there, you should have this expectation that you don't have to understand what happened in configure authorization or what's later on going to happen in configure clock. If you go to configure repository, you should again be met with a piece of code that respects the limitations of your short-term memory. So at most 7 things should be going on. So this is sort of just an idea that keeps on repeating. This is a little bit of an ad hoc enumeration, but the idea is that you should always have, if you can organize the code so that there's no more than 7 things going on, you have a much better chance of not having to rely that much on the long-term memory, and you can mostly rely on your short-term memory. Now, I promised to get back to this question of how do we ensure that things that have a level of complexity at one level of abstraction, when we look at it from the next level out, it should just look like one thing, because otherwise we can't have complexity leak through, because if that happens, the code no longer fits in our head. So we can, again, imagine that one of those cells is represented, for example, by this allocate method that we looked at before. And I would claim that the method not only fits in your head, but it also collapses into one thing. You can actually, as viewed from the outside, you can think of that as just one chunk of information. And there's a reason for that. Now, the first, before we do that, let's talk a little bit about the complexity, just to recap. So we already established that the cyclomatic complexity of this method is 3. So that's fine. That's well within the limits of our short-term memory. But again, if you imagine that this complexity leaks through, if you have to think about all 3 states, all three behaviors of this method, superimposed on each other, if you have to think of that when you call the allocate method, that means that you already expended 3 out of your budget of 7 in your calling code, so you can't really allow that sort of complexity to escape the scope of the implementation details. And if we want to use this crude method of just enumerating all the objects, I know there's really only one object that can actually change state, but if we just use the crude method of counting all the things, you'll notice that there are 6 of those as well. So you may be wondering now, why are there always 6 things in all the examples that I've shown you? And the reasons for that is that all the code that I've written for the book, I've followed this principle where, whenever I started to get near a threshold of 7, I would refactor the code so that I would always be, almost always be below 7 in terms of complexity. So often, if I have something where, there's 6 of something going on, I'm just letting it sit as it is. And then, if I add a 7th thing, I would often go and, prematurely refactor it so that it's ready to be changed again in the future. That's a little bit of a digression, though. But again, if we have 6 things going on here, we can't let, that knowledge that there's six things going on, you should not, as a caller, if you want to call the allocate method, you should not be required to understand that there are those six things going on, because again, if that's a requirement, the code is not going to fit in your short-term memory. So when we look at allocate from the outside, it must compact, it must collapse into just one chunk of information. That's how we need our brains to be able to treat it that way. And I believe that I can make the argument that this code fits that description. So the first thing is that this code has no side effects, this particular method. We can go back and look for side effects. So side effects are all the things that change the state of the system. So if you write a file to disk, that changes the state of the system. If you send an email to a customer, that changes the state of the system. If you're repainting something on the monitor, that actually changes the state of the system. So that's, if you write to the console, that changes the state of the system. Maybe. Okay. So there's a little bit of a philosophical discussion there. It's sort of like, if a tree falls in a forest and no one's around, does it make a sound? So it's a little bit like that. If you log to the console, but no one looks at the console, is that actually a side effect? Does that count or not? So you can sort of have those discussions, because there's always going to be the side effect of code executing that, electrons are going to move around in the physical world. So, some sort of side effect you always will have. But, noticeable side effects. There's no emails being sent here. There's no, files being written. There's no, screens being repainted here. Just some calculation stuff going on. So there's no side effects here. So that's one thing. Another property that this code has is that it's deterministic. So we define that as having the same inputs will always produce the same outputs. Let's go back and have a look at that again. So what are typical sources of non-deterministic behavior? So for example, if you rely on the system clock, now that's non-deterministic because the time changes all the time. So if you have code that relies on, it does a different thing if it's Sunday than if it's Monday, that's non-deterministic behavior. Or, if it checks the date or, the year or things like that, that's non-deterministic because it relies on the system clock. The same thing goes for random numbers. If you have any sort of random number generator involved, that's non-deterministic. It's almost, a tautology there. But also, if you do any sort of reading from I/O, if you read from a file or if you read from a database, that's also non-deterministic because, imagine reading from a file. The input is the file name, and you can go and read from the file and you return the contents. And then you have the same action one more time, the same file name, but then the contents of the file has changed in the meantime, so now you return something else. By the definition, the same input should always produce the same output. That's non-deterministic if you're reading from a file. So anything that performs I/O, so reading from a file, querying a database, querying a web service, all of that is also out of the picture. That's non-deterministic behavior. But we have none of that here. There's no random numbers being generated. We don't rely on the system clock. We don't do I/O. Okay. So together, we now have two properties. We have no side effects, and we have deterministic behavior. We call that a pure function. And this is interesting in terms of whether or not details leak, because pure functions are what we call referentially transparent. And what does that mean? So referential transparency means that the function call is equal to its result. So this from mathematics, that 2 plus 2 is always 4. And if I ask you, for example, what's 4 times 5? You'd probably say it's 20. And how did you know that? Now, you probably didn't actually perform the calculation. No, the calculation here is that you go 5 plus 5 plus 5 plus 5. You do that 4 times. That's the calculation. But you don't have to do that because you've memorized the multiplication table. Because the result is all you need. You don't need to do the calculation. You just need the result. And this is sort of the same thing here, is that if you know the inputs already, then you don't need to perform the calculation. You can just use the result. So the result is the same as the function. So going back to allocate here, this is a pure function. And that means we can regard all of this stuff as being just equal to the output it produces. It produces an enumerable table. That's basically a collection of tables. So we don't really need to understand exactly how it arrives at that. We just need to understand that the output of this function is just one thing. It's a collection of tables. So that's a chunk of information, a collection of tables. We can think of that as being one thing. So referential transparency is a really good way of making sure that things, that complexity doesn't leak. You can have a pure function that has cyclomatic complexity of 73 if that's what you want. But if it produces a single output, and what else can it do if it's a function? Now, that thing is just one output. And you don't have to think about, how did it arrive at that output. You can just think about it as the chunk of information. That's not, you can't write everything as pure functions. You also need other things as well. But, in general, we can say, how do we, design things so that, the complexity that's, inside of a thing doesn't leak through. We have a word for that. It's called encapsulation. This is the idea behind object-oriented encapsulation, is that you are not supposed to be, to understand the inner workings of an object. You're just supposed to be able to interact with it and not caring about how it's implemented. And if you want to implement it, you go and have a look at that implementation, but then you don't have to care about the callers or the environment, just the inputs and the outputs. So in general, encapsulation, and more specifically, write as many pure functions as you can. That's really going to help you, follow this design principle of not having too many things going on. All right. So to summarize, we need to be able to, organize code so that at every level, whether we zoom in or out, it should be organized so that it respects our short-term memory capacity, which is, about 7. We should be able to zoom in as we did before. We should be able to zoom all the way out to the entry point. But if we think about just some arbitrary level of abstraction here, again, our brains don't care about the abstraction level. We just need to make sure that we respect the constraints that we actually have in our brain. Now, obviously, we understand that even if we organize the code in such a way that there are only 7 things going on, within, behind each of those, 7 cells that we're looking at here, there might be more things going on. It's very likely that that's the case. So you might, for example, at the most, if we respect this design principle all the way through, at the next level down, there's 49 things going on, but we just don't, have to think about that in our short-term memory. But that's actually the case. But then, each of those, 7 cells might again, contain another hex flower, and each of those hex flowers might contain another hex flower. So this is a fractal, I call that the hex flower fractal. And if you came here and thought, fractal architecture is something with Mandelbrot sets or things like that, and you think this is not a fractal, here's another fractal that's very well known within the mathematical community. It's called the cock snowflake. It's quite obvious why it's called a snowflake, but you probably noticed that we basically just take each straight line and we subdivide it by adding, a little, triangular hump on it, and then we just keep on doing that. So you can keep on zooming in on the edge of the Cox snowflake, and it'll just keep on repeating the same pattern, forever. I stopped rendering at about 5 or 6 levels deep here, but that's the idea. And the same thing goes with the hex flower fractal here. I stopped rendering after 4 levels deep, because if I add a 5th level, I've tried, then it basically just becomes one green blob. So it's not that interesting to look at. But anyway, that's sort of why I call it fractal architecture, because it's actually, they are fractals, but it's more like a way of thinking about, how to structure code so that it sort of, keeps on respecting this self-repeating, self-similar pattern at all levels of abstraction. Because we only have that much capacity in our brain. In our short-term memory, you can keep track of 7 things, so we should write code that, respects that, code that fits in your head, which is also the title of my new book, which is right here, and you can get it wherever good books are sold. So that's basically what I have, but I left rooms for some questions and answers, and then if you don't have any questions and answers, you can get out of the room before everyone else. But for those of you who might be interested, I brought 2 copies of the book, and I'm going to give them away for people who ask nice questions. And I'm not going to be too discriminate. So basically, the first 2 people who get asks a decent question will get the copy of the book. So you can ask me basically something about the talk, or you can ask me about anything else. But if you have questions about something else, maybe wait with those until later. Are there any questions? Yes, sir.
So in one of the examples, the reservation example, you're using a property from within the class. Does that not end up you need to understand the restrictions of the class, like the level higher above, to know whether or not that property is going to have an impact, because maybe someone can come and try and change it underneath you, or maybe it's mutable or not immutable, and things like that.
Right. So let me try to rephrase this so that everyone else can hear it, and also to see if I understood the question correctly. So in one of the examples I show, I'm using a read-only property, the connection string. I suppose that's the one you're thinking about.
The initial list of tables.
Oh yeah, there's another example where I use a collection of tables, and I turn that into a list. That is also a read-only property, by the way. So your question is, if I'm sort of taking, properties or class fields into scope in my method, is that a problem? And what happens if other people come and change that later on?
Yeah, because I guess if the point of it is how much you have to keep in your head at once.
Yeah.
I have to already understand that that's a read-only property to
Yeah.
know that it's safe to.
Right. Yeah. So you further on say that in order for all of that to fit in my brain, I have to understand that this is a read-only property and it's sort of available in the class. Fair enough. Yeah. I think at the level of analysis that I showed, it's definitely a variable that is in scope. So in that case, it just counts towards my budget, if you will, and that's what I did. But you can also say at a slightly, if you take one step back and look at the overall object, the object should fit in your head as well, in the sense that you need to understand, what's actually available in the object, what sort of, read-only properties are there, or, settable properties, if that's the case, and what members are actually there. So I think this way of looking at things applies to all sorts of different levels. I showed you the public API of the startup class, for example, because I think it's important to also organize objects so that when you look at the public API, you don't want a list of 42 methods that is exposed by a given object, because then it becomes difficult to fit in your head again, because there's just too much stuff going on. And also it's pretty likely that an object like that is a God object that has low cohesion, so it should probably be refactored, but that's sort of like a different story. But I don't know if there's going to be any feedback if I come by and give you that. But you're welcome to come by and pick it up. Oh, you're coming right now, so I might actually just give it to you. All right.
Thank you.
Sure. All right. Anyone else? Let's see. Yes, there in the back.
Mr. Seemann, Mark, how does it relate to, for example, if we use polymorphism and we are close to modifications and if you extend to think classes?
Right. Okay. So the question. I'm sorry. Yeah. So you're asking, if I understand correctly, in the phase of polymorphism, interfaces or inheritance, you might have, a single interface, a single abstract class, but it might actually have, an unbounded number of, at least more than 7. Yeah. I think this is where thinking about, protocols become important. One of the things that I also talk about in the book is, around API design. It's quite important to think about invariants, so pre and post conditions. So this thing called the Liskov substitution principle, it tends to come in here because if you can imagine an interface, for example, you can say, hey, let's define an interface that my client code interacts with. And I might have various different implementations of that interface, but all the implementations must fulfill the same contract in the sense that the invariants must remain true. The preconditions and the postconditions exposed by each of those implementations must be the same. So the Liskov substitution principle says that things that are more derived should be, let's say, more. It's basically also the Postle's law. Must be more tolerant of input and more restrictive in output. So it's sort of like it keeps on fulfilling the same contract. So there's this idea of an interface on abstract base class representing a contract with some stated rules. And basically, that also means, again, that if you're looking at the call side where you want to call into an interface method, you should be able to think about that as saying, well, if I, as a caller, fulfill the preconditions, then I expect the implementation, whatever it is, to guarantee that the postconditions are going to be what they're supposed to be. And then again, exactly what happens and which one of the 21 implementations that I actually end up using shouldn't really be important at that level of granularity. So it still becomes just one thing, if that answers your question. I know that was a little bit of a ramble because I was trying to figure out, how to sort of answer the question. But I hope that I gave you a decent answer there. If I did, then please come and collect your book when you have the time. All right. I don't have any more books to hand out. I do have a few more minutes. So if you have more questions, then I'll be happy to. Yes, sir. Is there, I'm sorry, can you shout a little bit more?
Sorry.
Yeah, I'm getting old. My hearing is not as good as it's supposed to be.
Is there any point in the code base or just coming up with this model that you, like some point where you would actually abandon it because maybe it's going to come out just a bit weird, like lower quality code, or has it pretty much worked everywhere all the time?
Yeah, so if I may rephrase, just you ask, am I able to follow this, idea throughout, or, does it sometimes happen that I have to compromise on this principle for various different reasons? Is that a good, rephrase? Oh, okay, yeah, sure. I think I was, for the code base for the book, I think I was quite successful in following, this, most of those rules almost, throughout. And I said almost. And this has also been my experience with coaching teams and writing all the other, code, for production reviews. It's more often than not possible to follow this design principle. But again, it's an idea, it's a rule of thumb, it's a guiding principle, and I don't want to make it a hard rule that you must follow because you will always have edge cases, and I respect that edge cases will occur. But in my experience, you can follow this much more than you actually thought possible. But again, with exceptions, probably. All right, should we take one more, and then you can still get out of here before other people, or yes?
Is this an approach that would work alongside something like clean architecture, hexagonal architecture?
Yeah, right. Okay. So does this work with something like clean architecture, for example? So I must admit that I actually haven't read Robert C. Martin's book Clean Architecture yet, but lots of people have asked me about that. And as I understand clean architecture, it's very reminiscent of ports and adapters. Yes, those things I feel go very well together. All right, I think I'm going to let you off now, and if you want to talk to me, I'll just hang around here, and you're welcome to come and talk to me. But thanks for coming.